Okay, in this video I will walk you through an introduction to permanent magnet DC motors. A permanent magnet DC motor, or APM DC motor, is a DC motor whose poles are made of permanent magnets. So in contrast to other types of motor, this motor have permanent magnets rather than electromagnetic windings to generate the magnetic field. The advantages of these motors are they are generally less expensive, smaller in size, and more simple than other types of DC motors because they don't have the additional winding. The connection is generally less, and this also makes the motor more simple in general. The disadvantages of this type of motor: generally its flux is not as high as the other types. This is especially true for larger size or larger machines. Yeah? For smaller machines, it's not necessarily true, yeah, because we can have a strong magnets to generate the high flux. And the other disadvantage of this type of motor is that it has a risk of demagnetization because it's using permanent magnets, and permanent magnets can lose its magnetic property, yeah, because of two factors. One is it could be because of the existence of an additional or other magnetic field surrounding the motor, and the other possibility is that if it gets overheated, yeah, because magnets or permanent magnets have normally limitation in terms of its operating temperature. Some magnets can survive in a temperature up to 150 degrees, while the other more specific types of magnets can survive more than 200 degrees, but this type of magnets is more costly compared to the ones that can survive for more limited temperature range. And this figure here gives us the illustration of a permanent magnet DC motor. As you can see, it has this stator magnet, yeah. So in rather than winding, it has these permanent magnet poles to generate the magnetic field. For the equivalent circuit, again, you can see that it's a very simple one. It's got only armature circuit. It doesn't have the field circuit, and we can easily derive the equations from this equivalent circuit by using KVL. We can see that VT is equals to EA plus IARA. IA is the armature current flowing in this direction here. Yeah. So VT is equals to EA plus IA RA. Okay, and for the currents, you can see that IL is simply equal to IA. Okay. So line current equals to armature current. Okay, and finally we want to discuss a bit on the speed control. There are two different ways to control the speed of this type of motor. If you remember, when we discussed the speed control for shunt DC motor, there were three different types, while we've got only two here because we don't have any field circuit, which means that we cannot control the speed by using the field resistance. So we got only two techniques, which are the the terminal voltage VT control and the armature resistance or RA control. And we can see, if you remember, that we have this equation: internal generated voltage is equals to K prime into flux into N, while these first two are actually constant, so we can replace it with K2 prime if you like, and then as a result we have a more simple equation for this permanent magnet DC motor, which tells us that the EA, or internal generated voltage, is directly proportional to the speed. So if we want to control the speed, then we want to be able to adjust the internal generated voltage. And from this equation we can see that we can achieve this by either changing VT, or we can also achieve it by changing RA. So these are the two techniques that we use to control the speed of a permanent magnet DC motor.